A paradox, according to Merriam-Webster, is a statement that's seemingly contradictory or opposed to common sense, and yet is perhaps true, or b, a self-contradictory statement that at first seems true. So, is it something that seems true but is contradictory, or is it something that seems contradictory but is true? Can it be both? They're opposites, so that seems to be contradictory, right? And yet it's true. Or is it the other way around? Isn't that the definition of a paradox that we just defined? The definition of a paradox is a paradox and hence self-referential. Can something be two things at once? How do you define something? Definitions, paradoxes, and self-reference will all be pivotal in this presentation. First, let's refresh everyone's minds on what diagonalization is. Take a set of innumerable numbers and list them out in some order. To create a number that's not in the list, take the first digit of the first number and tweak it. Take the second digit of the second, the third of the third, and so on, and tweak all of them. There are several ways of tweaking a number, but here I'll keep it simple and say incremented by 1 if it's anything other than a 9, and decremented by 1 if it's a 9. The number that's created from this differs from every number in the list, regardless of the length of the list, by at least one digit. i.e., it differs from the nth number at least at the nth digit. Therefore, it's a number that cannot appear in the list. Now that we've got this refreshed, let's look at Richard's paradox. Jules Richard was a French mathematician. He mainly worked on geometry, but his name is associated a bit with the paradox that he wrote about and published in 1903. The paradox goes as such. Take the set of all definable numbers. This is any number that we can define with a string. For example, 3.456, 1, the number after 41, pi, etc. We can order all those definitions quite simply, by alphabetical order. Now, order every single one of the numbers in alphabetical order of their definition, and apply a diagonalization argument to these. You get a number, nu, that's therefore not in the set of definable numbers, even if the set is infinite, as it differs from every single number by at least one digit. Therefore, nu isn't in the set of definable numbers. It's different from each of them, so it's not definable. But did I not just define it nu? If you take exactly what I just said and put it as a string, isn't that the definition of nu? Nu is definable, but it's also not. Now that's a paradox. It's easy to see that this poses a problem. There's a contradiction. We will go over the exact explanation of the underlying problem later on, but for now, perhaps the answer lies in that natural language is too vague to define any sort of consistent mathematical concept. So what can? Let's travel forward a few years to the 1920s. In that period, David Hilbert set out a goal, Hilbert's program. His aim was for all mathematics to be as unshakable by these types of paradoxes as possible. He wanted to formalize mathematics in a system that was to be consistent, complete, and decidable. Similar to Euclid's geometry, his system would be based on axioms, formulae in the system that are taken to be true and often evident. Consistent means that from the axioms, one cannot derive both the formula and its negation. So, essentially, you cannot derive a contradiction. So, here, for all formulae P, it's not the case that one can derive or prove P and derive not P. This isn't standard notation by any means, it's just to illustrate the concept. Complete means that for every statement, either it can be derived from the axioms, or its negation can. i.e., for every well-formed statement, either it's a theorem of the system, so it's provable in the system, or its negation is a theorem of the system. In other words, for all P, either P is derivable or not P is derivable. Decidable means that there's a procedure or algorithm that can determine whether a formula is a theorem of the system. So there exists some algorithm such that for all formulae P, that algorithm tells us whether P is a theorem of the system. Hilbert famously said, "We must know, we will know," a quote which is now written on his grave. Unfortunately for Hilbert, while we might need to know, we shan't. Little did he know at the time, but his dream of such a beautiful system was going to be shattered, and rather quickly. As you probably know, any sort of decently powerful system of mathematics is incomplete. There comes Gödel's incompleteness theorem. Gödel is a fan of self-reference. It's easy to do in natural language, especially to create paradoxes. For example, the famous liar's paradox. This sentence is false. This is a reference to the sentence itself, making a loop and making the statement a paradox. If it's true, then it's false. If it's false, then it's true. But what does that have to do with completeness? How do you create self-reference in maths? This bit will get a bit more technical. Firstly, Gödel encodes every possible formula with a unique number. That is, he creates a function g from the set of formulae to the natural numbers. Each sentence therefore has a unique Gödel number. He does this by encoding a number for every symbol and its position. He gives a number to every symbol, as such, and assigns every position a prime number. So, for example, the first position is 2, the second is 3, the third is 5, and so on. Then, he puts the number of the position to the power of the number assigned to the symbol. That was confusing. So, to show this, let's use an example. For all y equals y. Fairly simple formula. It's true, but it doesn't matter. Take all the symbol's position numbers, so for the opening bracket, this would be 5, and put them to the power of the symbol's number. This creates an absurdly large number, even for short sentences, but enables each number to be unique, as prime factoring a number will give you instructions on how to find the sentence. He also does this to sequences of sentences, by doing the same system, but using the prime numbers as positions of the sentences in the sequence, and the powers of the Gödel numbers of the sentences in that sequence. Short aside, we won't use our normal numbers in the formula language, as that would be hard to arithmetize, ironically. So we'll use the following system. 0 is 0, and if you add an s in front of a formula representing a number, it's the number plus 1. So SO is 1, SSO is 2, and so on. Those can be encoded by a Gödel number as well, using the technique we found before, as they're also formulae. Now that we have an encoding of every single formula and sequences of formulae into natural numbers, every rule of inference can be treated as an arithmetic operation between two numbers. For the sake of clarity, for this bit, expressions which are numbers will be represented in red, and formulae in the logic language will be represented in blue. So, for example, if we take the rule of inference in propositional logic of AND, we can say that this is represented by a very, very complicated operator, which we'll represent here by this symbol, the plus within the circle. All instances of the rule for AND translated into numbers can all be explained with this operator, which takes the numbers of any phi m psi and outputs the number which represents the formula phi m psi with an AND in the middle. Back into the formal language itself, we can now make a predicate, which will abbreviate P, which takes three numbers in arithmetic and returns true if they satisfy the arithmetic operation. We can make P because we can formalize the arithmetic operator, or function, into the system, as the system can formalize any natural number function, because it's a system that has the power of arithmetic. This essentially says that the formula represented by the number z is derivable from the rule AND, from the formulae with Gödel numbers x and y. Remember, x bar here isn't a number, it's a formula with an SSSSS and an O representing a number, which further represents a formula. Now, do this for every rule of inference. These are fairly complicated predicates, but we can make them. Just to recap, we've managed to translate every formula in numbers, and managed to translate every allowed step in logic. So anything that follows from these arithmetic operations is a number that we can get via a proof. This means that we can also make a binary predicate, proof XS(x), that takes a number XS that represents a sequence of formulae, and X, which is a formula, and checks whether each item in XS follows either from previous items in the list or is an axiom, and sees whether X is part of the sequence. This essentially means that it checks whether XS is a proof of X. We know that this is theoretically possible, as every small instance of the functions that make up proof XS(x) are easily computable within natural numbers, and this is just a vast agglomeration of them. Obviously, the function is hilariously complicated, but we'll write it as proof XS X. Now, take the sentence, there exists a Y such that proof YX. Now define a predicate prove X, which is equivalent to that sentence. As you can see, this basically means X is provable. Let's define one final function, and we'll almost be there. Hang on. Let's define sub, the substitution function. Sub takes this time 3 inputs. Let's call them M, N, and X. Sub takes the sentence with Gödel number M and replaces every instance of what's represented by X with N. This is it written out. Feel free to pause if you want to understand it properly. So, let's say Y has Gödel number 17. Sub MY17 is the identity function because it takes the sentence with Gödel number M and replaces every Y with Y. Alright, we've got all the tools to make G now, the magical self-referential statement. Take the sentence, not prove sub YY17. Don't try to understand what it means yet, it doesn't matter. Just know that because it's going to be represented by a string of symbols, it's going to have a Gödel number, which is also huge. Let's call this number n. Now, take not provable sub NN17. Now what does that mean? Well, let's remember that sub outputs a number. So sub NN17 outputs some number. Let's call it G. Therefore, not prove sub NN17 says that some sentence represented by the number G doesn't have a proof. It's unprovable. So G is unprovable. But what is G? What sentence does it represent that's supposedly unprovable? Let's remind ourselves of what this means. It takes the sentence with Gödel number n, so this one, and replaces every instance of Y, because Y is represented by 17, with n. What happens when you replace every Y with an n? Well, you get this. Just think about it. If you take not prove sub YY17 and you replace every Y with an n, you get not prove sub NN17. So sub NN17 is the Gödel number of the entire sentence, i.e. G, which is sub NN17, represents this sentence here. Take a moment to take this in. Therefore, if the sentence says the sentence with Gödel number G is unprovable, but it itself is the sentence with Gödel number G, then it's saying, I am unprovable. Now, we have two options. Under our interpretation, either the sentence with Gödel number G is false, so its negation is true, i.e. G is provable. This is the negation of G, and it's true. Now, since not G is true, then the system proves G. Either not G is also provable, so the system is inconsistent, or not G is not provable, but since it's true, we've got a true, unprovable statement. Alright, fine, but what if G is true? Well, then that's easy. If it's true, then it's unprovable, as it states itself. And we still have a true but unprovable statement. So either way, the system has some statements that are true but unprovable. And unless the system can prove false things, G is true. This technique may have seemed convoluted, but it actually follows pretty plainly from a simple rule. The diagonal lemma. For every formula P with one free variable, then within the system, if there's a Gödel number in G, then there exists a sentence A, such that A, if and only if, f G of A. A is called the fixed point of the function f. Gödel's first incompleteness theorem is an instance of this, where A is the sentence G, and f is the function that says that its argument is unprovable. We have now seen that in a consistent formal system, some formulae must be true even though they are unprovable within the system, at least if the formal system can have a Gödel numbering and therefore be powerful enough to support basic arithmetic. But what does it mean for something to be true if it's unprovable? Well, a formula is true in a model if the model satisfies the formula. Maybe there's a way of formalizing this concept of truth, even if that's not via provability. However, this won't work either, not within the system. As Alfred Tarski showed in 1933, truth is not definable within a system. Let's assume we had a predicate, true x, which was defined as true x if and only if x holds in the interpretation. Now back to diagonalization. True will apply here, but so will the predicate not true. We can prove that not true, A, if and only if A for some A, which is the contradiction of the definition of the predicate. Well, then we can't formalize truth within a system, but we, as entities outside of that system, can see whether something's true, no? For example, we can see that the sentence with Gödel number G must be true and unprovable. This is assuming the axioms are true, and the rules of inference cannot lead us to something false from something true. But if G is true and unprovable, shouldn't it be an axiom too? Eureka! This would make math complete, right? Just add every unprovable truth as an axiom, and no truth will be underivable. Well, unfortunately, that doesn't solve our problems either. Take the original axioms that we used to make G. They build a formal system T, from which we can derive G from Gödelization. If we add G to those axioms and make a new set of axioms, we get a new system, T apostrophe. But now, we can Gödelize this system again, so it gets its very own Gödel number G apostrophe, which is unprovable but true within T apostrophe. As you can see, this runs forever. And anyway, how do we even decide whether an unprovable statement is true or not? Well, back to what truth means. Formally, that's if it holds within the structure, or interpretation. Sure, but what's the right interpretation? Well, it often seems obvious, but not always. It's just what the formula actually means, right? Well, what the formula means is not exactly objective. It might seem extremely difficult to see how 1 + 1 = 2 could mean something different than what you probably understand it as, but if we take a slightly more visual example, you will see how different additions of axioms can create different realities and models. Earlier, we briefly mentioned Euclid's geometry. It's made up of 5 axioms. 1. A straight line may be drawn between any 2 points. 2. Any terminated straight line may be extended indefinitely. 3. A circle may be drawn with any given point as a center and any given radius. And 4. All right angles are equal. The 5th axiom is a different sort of statement. If 2 straight lines in a plane are met by another line, and if the sum of the internal angles on one side is less than the 2 right angles, then the straight lines will meet, if extended sufficiently, on the side on which the sum of the angles is less than the 2 right angles. Phew. Clearly, the 5th one is longer, more complicated, and generally seems inelegant. Many mathematicians tried for a long time to derive the 5th axioms from the previous 4, with no avail. It is in fact a statement that neither it or its negation can be derived from the other axioms, like G in arithmetic. So what happens if you don't include this axiom, or rather, if you include its negation? Does it matter? Does it make the system invalid? Well, it does matter, but it doesn't make the system invalid. You just get, you guessed it, non-Euclidean geometry. For example, you get something a little crazy. A triangle with 3 right angles. For the system to make sense, we just need to interpret it differently. You need a different perspective. Hence, some statements like the angles of a triangle add up to more than 180 degrees aren't false. They just need a different perspective, a non-Euclidean triangle. So, can we just decide whether an unprovable statement should be added as an axiom? Kind of, but not really. Within a structure or interpretation, an undecidable sentence is still true or false. All it means for it to be undecidable is that there are at least 2 structures under which all the decidable statements keep the same truth value, but the undecidable statement's truth value changes. So, if you add an undecidable statement as an axiom, you might have to change the structure that you're looking at. Or you don't have to. It depends. Sometimes that change will be quite big, like Euclidean versus non-Euclidean structures, and other times it won't matter much. The structures that we choose for our systems are only there so that we get something out of the system in the most useful way possible and helps us model the world. Cool. But wait a minute. We've left out a part of Hilbert's program, no? Decidability. The idea that there's an algorithm that can see whether a formula is provable within the system or not. After all, these unprovable statements may be unprovable, but surely we can have a reliable way of determining that they are unprovable, right? Well, as for the final blow to Hilbert's program, in fact, we can't. Perhaps the best way to show this is through Turing's 1936 paper on computable numbers and an application to the Entscheidungsproblem. This presentation doesn't have the scope to explain it all, but here it goes in broad strokes. Turing first describes Turing machines, machines that read symbols on a tape and output numbers 1 and 0. It follows a set of instructions. It has a set number of states and a set number of actions, such as move right, print a symbol, move left, change state. The actions are deterministic. For example, when it's in state Z and on a little square on the tape with symbol 1, it will do actions of moving right and printing or changing whatever is there to a 0. All the numbers it is able to print in this fashion are what Turing calls computable. In fact, a Turing machine can simulate any algorithm, but we can't prove that here. We'll focus on computable numbers. All these computable numbers might also be called definable. They can be defined by a finite set of instructions that a Turing machine will obey to print that number. Turing then assigns each Turing machine a number similar to how Gödel gave each of his formulae a number. Since each computable number is associated with at least one Turing machine, and the Turing machines are enumerable by ordering their instructions methodically, hence, so are computable numbers. He then crafts a universal Turing machine, which takes as an input a Turing machine number, somehow translates it back into a set of instructions, and simulates it. It outputs the number of the Turing machine it got fed. Don't worry how it works. It doesn't matter here, and Turing outlines exactly how to do it in his paper. But wait, can't you diagonalize this too? Whoa, where did I pull that from? Well, let's say you found a way to order the computable numbers. In fact, we should be able to, right? The instructions are finite, so we should just be able to order them in some sort of order, maybe by alphabetical order. Then you could run a diagonal argument on them and find a contradiction. Here's how it would work. Set n to 0, which is the digit index, and c to 0, which is the machine integer. Increment c, and then check whether c is a valid machine integer. If it's not, then increment c and try again. If it is, decode the machine MC, and then check whether MC is a circle-free machine. If a machine is circle-free, it essentially means it won't go on an endless loop without printing anything. So it will actually print a number. So if it's not, then again, increment C and do it again. If it is circle-free, that means it will not go in a loop forever. Increment N. So that means that we are at the nth machine. Now generate the nth digit with a universal Turing machine simulating MC. Tweak the digit and print the result. This is an algorithm, so it should be able to be simulated by a universal Turing machine with number t, and it's essentially a diagonalization argument on all computable numbers. What is essentially happening is that you're taking the nth machine, printing the nth number of that machine, and tweaking it. So the number that's computed shouldn't be in this set of computable numbers. Except we just computed the new number with that Turing machine t, because it's an algorithm. So surely the number's computable. But it can't appear in the list because it differs from every computable number in the list by at least one. What went wrong? Well, let's visualize this. On the left is the xth machine, represented by n in our algorithm. Here is the machine number represented by c, and here is the number that machine outputs. Let's say our algorithm can be run on a machine with number t, and it's the mth machine. What it will output is the first digit of the first machine tweaked, the second of the second machine tweaked, etc. until it reaches itself. When it reaches itself, it will have to print the nth number of itself, tweaked. Except we are at the nth digit. So it's printing the nth digit, the digit that it should print, but tweaked. That's clearly a contradiction. So the only conclusion here is that machine T isn't possible. Something must have gone wrong. But where? Here. We can check that all of these steps can be done. Turing shows it in his paper. The only one that is the weak link is this step, checking whether the machine holds or goes on a loop forever. This is the halting problem. One cannot have a procedure or algorithm that can determine in finite time whether any Turing machine will halt. This is actually analogous to why not every unprovable statement can be proven in finite time that it is unprovable. There's no general algorithm that can decide whether a set of rules, in this case the rules of inference, from axioms, will eventually find the proof we want, or the number we want, which means it's either provable or it will run forever, which means it's unprovable. Therefore, maths is also undecidable. That was a lot, but before we end this and go a bit lighter, I'd like to quickly go back to Richard's paradox. Do you remember it? The one about definability? Well, to refresh your memory, here it is again. We earlier said that this is because definability is vague. In a way, yes. So let's formalize definability and see where this goes wrong. Let's say that there is a specific set of rules T that enables us to get a number from a definition if it's a valid definition. Now for a proof by contradiction, in order for the paradox to work, let's assume these rules also tell us which definitions are valid definitions. We're going to show that this thing is not possible. The rules of T cannot also determine which definitions are valid definitions. If there's some string that defines a number x, we can call that number T definable. Since every definition is a string, they can be ordered. Because of these 2 points, there must be a T definable function f that takes a string and a number and outputs 1 if that's a valid definition for x and 0 otherwise. From this assumption, we T define a function sumDef that outputs 1 if and only if there's a definition for x, i.e. if for some string fsx equals 1. Then, T define string number n to be the nth string if we order them. Then, T define definition number m to be the sum of sumDef string number k over all k until m. This means that if you give definition number a string number, it tells you how many of the strings before it are definitions. So, if I give it 100 and it gives me 4, that means that if I take the first 100 strings, 4 of them are valid definitions for numbers, or valid T definitions. Then, T define min n to be the minimal m such that definitions m equals n. So min n is the string number of the nth valid definition. Finally, define xn to be the real number T defined by the string with number min n. If you want to pause, write this down and have a look, feel free. If you haven't followed, don't worry. In words, from the 2 assumptions, we have shown that we can formally get the following. String number min m, which is the nth string that makes T sense, i.e., it is a valid definition according to the rules of T. xn is the number defined by that definition, so the nth T definable number. Since we've shown that they're possible formally within the rules of T, these notions make T sense and are definable in T. Now, we apply an explicit T definable diagonalization argument to this list, and come to a contradiction once again. The T definition of the diagonal number created must be in the list somewhere, but since it differs from every number in the list by at least 1 digit, it cannot be in the list, therefore it cannot be T definable. Hence, there is the proof by contradiction. That second assumption about the rules of T can't be true. You cannot, within the rules of definability, define and make up what's definable. This is in fact analogous to Turing's halting problem. Definable is analogous to computable. The rules T simply represent the rules of a universal Turing machine. Let's see how it swaps out. If the rules of the universal Turing machine allow you to compute what number is computed by a circle-free Turing machine, then you cannot have the second line, which is that you can also compute which Turing machines are circle-free. In this case, valid definition is a circle-free Turing machine. A computable number is a number with a definition, or a definable number, and defining is computing, while strings are Turing machines. This is how you get from a philosophically seemingly silly paradox to Turing, who, on the shoulders of other philosophers and logicians, set up the technology we use today. All of that while discovering strange realities about the mathematical world. And that's why philosophy and computer science is cool.